Hello, and in this video we'll talk about ordinary least squared method in matrix form, how we can find our optimal coefficients for our linear regression model. And the design matrix X has size n and k, where n is the number of samples and k is the number of features. So that is our matrix X, uh, basically our data set of our features and objects. And we can write our MSC for MSC equality functional in a matrix form. Basically, it will look like X again is our matrix. The coefficient vector like beta 1, 0, second coefficient beta 2. We have our target vector with our target values related to our X objects. And T is transpose, so we transpose this, we flip, columns become rows, rows columns, and here is our original, the same matrix without flipping. And what we basically do the same, we divide the whole thing by amount of samples that we had in our data set, in our training data set. Basically, when we do multiplication of transform matrix into multiply by original matrix, we will get squared result. And we can see below just all our rows that we had, this row, this row and this row, they become squared and summarized together. So you got, so basically just we got vector of our loss functions for each individual object divided by 3. So we got the same MSE like this. So basically we got the same one, the same quality functional that we had in the last ordinary square lesson. And the next step will be the same. We have to find partial derivatives for each of our coefficient that we have that is changing, that is the on which our y is dependent. And then we will solve system of equations and we will find best coefficients. We will find those coefficients that are in our minima point. Pretty the same stuff, but now we have it in the matrix form. So basically, matrix form of OLS, this is our matrix form of our quality functional, and we want find the minima of this. So we have to calculate partial derivatives for each coefficient, and we can get the same answer, plus 5 minus 30 minus 45. And how we get this, there are some ways how we can find matrix derivatives, but they might be difficult. I'm not familiar with them. I never worked with them. So in this lesson, we will use a prepared formula that we have that explains how we can find the same best coefficients for our model, the same minima point of a quality functional by applying this formula. And what we just achieved by expressing linear regression in matrix form, we've gone from a hand-solved example to a general algorithm that works for any number of features and any data set size. So this normal equation, our vector of weights equals to parentheses x stands for multiplied by original x, and this is the whole. This the answer of this multiplication is inversed multiplied by x transformed multiplied by our vector of our targets. So this is a formula of foundation of OLS, ordinally squared method regression. In practice, you'd use linear solve rather than explicit computed inverse for this particular part, but mathematics is identical. This concludes our explanation of linear regression in matrix form. So basically, we found quality functional. We are looking for partial derivatives, find their minima, and we use closed form solution. And by these calculations, we got the same three coefficients beta with the same values. So in next lesson, we will practice this on Jupyter notebook.